Hello guys, welcome to the chapter 4, Multi-Degree of Freedom. I don't understand why is that. Multi-degree of freedom is a system whose motion is described by more than one generalized coordinate, DOF. At the end of this session, we will be able to understand the multi-degree of freedom spring mass system, derive equation of motion using Newton's second law, derive equation of motion using Lagrange equations, solve time response of free undamped system, understand mode shifts and solve natural frequency, obtain harmonic response of the system. Okay, let's proceed to the number 1. Understand the multi-degree of freedom spring mass system. For your information, most engineering systems are continuous, they possess infinite degree of freedom. It requires solving partial differential equations, which is difficult to do. Therefore, a simplified continuous engineering systems are represented as definable degree of freedom. Yay! Replace the distributed mass and inertia by finite number or lump mass or body. Okay, we go to the number 2. By using Newton's second law to derive equations of motion. First, we must set up suitable coordinates to describe the positions of various point mass. 2. Draw the FBD for individual mass. Then, we apply Newton's second law of motion to each mass. For translational system with mass, mx double dot equal to summation of force, and for torsional system, j theta double dot equal to summation of moment. For example, consider spring mass damper system as shown as below. The FBD for any one element can be as following. By applying Newton's second law for the mass with Ft is 0, we can arrange the equation and set the equation equal to 0. If we have n number of mass, then we will have n number of equations. Then, we can express the above equation into the metric form. From the general equation, mx double dot plus cx dot plus kx equals 0, where m is mass, c is damping, k is stiffness. It is given by, we can see the metric form of the mass, spring stiffness, and damper stiffness. We proceed to the number 3, which is Lagrange method. Lagrange equations It used energy method to derive the governing differential equation of motion for the vibrating system. Lagrange equation also can be stated for n degree of freedom system as where q dot equal to del q over del t is generalized velocity. Q the power of n is non-conservative generalized force corresponding to the generalized coordinate and may be dissipative damping force or other external forces. For example, the question is, use Lagrange equation to derive the equation of motion for system shown below. For the solution, the potential energy at maximum deflection, we can see the equation of the potential energy at maximum deflection and the kinetic energy at equilibrium. We can get the equation of del t over del x equal to del t over x, del t over x equal to 0. After we get the equation of the u, we must differentiate the equation of u. Then, we use the metric form. We proceed to the number 4. Time response of free and undamped system. Mx double dot plus Kx equal to 0 without Cx dot. To solve, time response generalized into which x is modal vector mode shape, a is constant amplitude, omega is natural frequency, alpha is phase angle constant. At initial condition of t equal to 0, constant amplitude and constant phase angle can be determined at t equal to 0 after first order differential with respect to time. Suppose I equal to 3, which is 3 degree of freedom. We go to number 5, natural frequency, which is known as eigenvalues, and natural modes, which is eigenvector. General equation for the linear, undamped, and degree of freedom system given by mx double dot plus kx equal to 0, where m is mass, K is stiffness symmetry of nx n matrices, x is n-dimensional column vector. The normal solution is given by xt equal to x exponent I omega t. X contain dimensional of constant called mode shapes. Each natural frequency, which is omega, has at least one corresponding mode shape. Then, we sub of equation 1 into 2, which is negative omega square mx plus kx, in bracket exponent I omega t equal to 0. Since exponent I omega t is not equal to 0, where k minus omega square mx equal to 0 is called eigenvalue equation from k minus omega square mx equal to 0, and by letting lambda equal to 1 over omega square, then become lambda k minus mx equal to 0. Pre-multiplying the above equation with k, the power of negative 1 lead to lambda minus k power of negative 1 mx equal to 0. and replacing d to k to the power of -1 m led to equation eigenvector equation, which is lambda minus dx equal to 0, where I is the identity matrix. The frequencies can be solved by taking the determinant equal to 0. Eigenvector will give sets of mode shape, where the mode shapes is deposit to the number 6 harmonic excitations. The differential equations governing the motion of n degree of freedom for undamped system is mx double dot plus kx equal to f sin omega t. The particular solution is in form of xt equal to u sin omega t. Substitute into the equation of motion negative omega square m plus ku equal to f. The solution for the above equation can be written as the steady state amplitude are chosen to be positive. If negative value is obtained, say ut is less than 0, the response of system is written as, for example, of question. We can see the FBD and we derive equation of motion. Assume x2 is bigger than x1. And we proceed to Newton's second law of equation. We proceed to the metric form. For the Lagrange method, T is total kinetic energy, while U is total potential energy. Q is external force or damping force. Substitute 1 and 2 into the equation. Then we substitute 3 and 4 into the equation. By applying metric into equation 3 and 6, eigenvalue, which is natural frequency, for example, then we assume lambda equal to omega square. Then solve by using calculator. Then we will get lambda 1 equal to 17.07 rad second and lambda 2 equal to 2.93 rad per second. We use the formula of the lambda 1 equal to omega square. Then we will get the value of the omega 1, which is omega 1 equal to 4.13 rad per second, and omega 2 is 1.717 rad per second. Agent vector. From equation 1 and from equation 2, for the first mode and the second mode. Alhamdulillah. Thank you for watching.